Hey, I want to finish up our discussion of integration by parts by looking at a couple of examples that are slightly trickier than the ones we did last time. Okay, let's consider the integral of x squared e to the 3x dx, an integration by parts problem. And our first step is to choose our u and dv, and if we set u equal to x squared, then we have no choice but to set dv equal to everything else, e to the 3x dx, so that what we have is the integral of u times dv, x squared times e to the 3x dx. All that's left is to find du and v, and since du dx is 2x, du is 2x dx in differential notation, and v is the integral of dv, so the integral of e to the 3x dx. That's a substitution problem. Go off, do it on your own on the side, let r equal 3x, and you'll find that v is equal to 1/3 e to the 3x. This kind of problem, the integral of e to the 3x, comes up very often, to the point where you may find that you memorize the answer. It's easy to check. Take the derivative of 1/3 e to the 3x and you'll get e to the 3x. The problem with memorizing the answer like that is that half of you will memorize the answer incorrectly and you'll write 3e to the 3x there, which is completely wrong. And so for at least a while, get in the habit of going off and really doing the substitution. Let r equal 3x, work through the steps, and get to the point where you get that v is 1/3 e to the 3x here. And then when you're completely confident that you know the answer, I don't need to see the work for that. But if you don't show the work for that, then you better get it right. The formula for integration by parts then tells us that our original integral is equal to u times v, that's 1/3 x squared e to the 3x, minus the integral of v du, which is 1/3 e to the 3x times 2x dx. Pulling out the constants and then rewriting e to the 3x times x in its more usual form, x e to the 3x, we now see that in order to compute this integral, we need to figure out the integral of x e to the 3x. And you could argue that, well, you started with a difficult problem and you ended up with a difficult problem. And so maybe we chose our u and dv wrong and should go back and make a different choice for u and dv. And you could try that. It won't get any better. What's really happened here is we started out with a difficult problem and we ended up with a simpler integration by parts problem. The integral of x e to the 3x dx is an integration by parts problem a little bit easier than the integral of x squared e to the 3x dx. And so we have to apply integration by parts to compute that integral. And so we can go off on the side here to compute the integral of x e to the 3x dx. Doing it by parts, we let u equal x. dv has to be everything else. It's e to the 3x dx. And in this case, du is just equal to dx, because du dx is equal to 1. The derivative of x is 1. And so in differential notation, du is just equal to dx. And we already computed v in the case where dv is e to the 3x dx. That was over here. And so there's really no reason to do that work again. In other words, we did it maybe carefully by substitution the first time. It hasn't changed. The integral of e to the 3x dx, still 1/3 e to the 3x. So don't do that work again. If you've already done it once, just take advantage of the fact that you've done it and write down the answer. And applying the formula for integration by parts, we get that the integral of x e to the 3x dx is equal to u times v, that's x times 1/3 e to the 3x. It would look silly that way, x times 1/3 e to the 3x. We pull the constant out in front and write that as 1/3 x e to the 3x, minus the integral of v du, and v is 1/3 e to the 3x, and du is just dx, and so you can see I've written that integral there. I've just pulled the 1/3 outside of the integral. And once again, we've already computed the integral of e to the 3x dx. We did it when we found v just a moment ago and also in the original integral. The integral of e to the 3x dx is still 1/3 e to the 3x. And combining the constants, we get this result right here. Remember, this is just some work that we did off on the side to compute a piece of the original integral, in particular this piece right here. And so now we have to go and plug the result that we came up with, this thing right here, in for, the piece that we were working on over there. You have to be a little bit careful. The 2/3 in front of the integral is multiplied by the entire result, although I've pulled the constant outside what we're multiplying by the 2/3, because 2/3 times a constant is just a different constant. And after carefully distributing, you get this result right here. The moral of the story: you might have to apply integration by parts more than once in an integration by parts problem. In fact, it's even worse. Consider this integral, the integral of x to the 10th times e to the 3x dx. If you applied integration by parts and let u equal x to the 10th and dv be e to the 3x dx, it would work just the same way, and you'd come up with some new integral that included an x to the 9th e to the 3x dx, which is an integration by parts problem where you'd let u equal x to the 9th and dv be the rest. And after you applied integration by parts, you'd come up with some new integral that had an x to the 8th e to the 3x in it, etc., etc., etc. And you'd apply integration by parts 10 times in order to finally come up with some horrible answer. On the other hand, the good news for you folks is that, when I'm giving you a quiz or an exam and I want to check to see whether or not you know how to do integration by parts, your time is limited. It's probably not the only thing I want to check. And if I can see that you can do integration by parts, I don't really need to see that you can do it twice or 3 times or 10 times. And so these problems where you have to apply integration by parts more than once, like the one we just did right here, perfectly reasonable homework problems. And in fact, you really ought to do 1 or 2 of them for homework just so that you see how it's done. Lousy quiz and exam problems. So don't expect to see them on quizzes and exams. Do expect to see them on homework. Okay, you try this one just for practice. We'll go over it in a minute. Some of you will see that you could certainly pull the 7 out and just work with it as x squared times the cosine of 5x. That works fine. The only problem with that is sometimes people pull the 7 out and then forget to put it back in at the end. They do some tremendous amount of work and then forget to multiply the whole thing by 7 in the end. And so why don't we all start with u equal to 7x squared and go from there, and that way we all come up with the same sort of steps along the way. So pause the video, work this out. When you're ready, start it up again, and we'll do it together. If u is 7x squared, then dv has to be the cosine of 5x dx, in which case du is 14x dx. Don't forget your dx's, they're important. They're what lets us integrate the piece that we come up with after we apply the formula. And v, after you integrate dv, is 1/5 the sine of 5x. Go off on the side and do that by substitution and make sure you get it exactly right. Applying the formula for integration by parts gives us that our original integral is equal to this expression here, which is u times v minus the integral of v du. And then we have to compute what is the integral of x times the sine of 5x dx. Well, that's an integration by parts problem. We go off on the side to work on that. We set u equal to x and dv equal to the sine of 5x dx. So that du is equal to dx, and after you carefully integrate dv, you find that v is negative 1/5 the cosine of 5x. And once again, applying the formula for integration by parts, we get that the integral of x times the sine of 5x dx is u times v, which is negative 1/5 x times the cosine of 5x, minus the integral of v du, and subtracting negative 1/5 is adding 1/5. We'll pulled the 1/5 outside the integral, and you just end up with the integral of the cosine of 5x inside there. We've already integrated the cosine of 5x over here when we figured out v, so the integral of the cosine of 5x is 1/5 the sine of 5x. And that gives us this result here for the integral of x times the sine of 5x dx. We're now ready to plug that back into our original problem so that we can come up with the answer to that original problem. And after you plug that answer back in and do a lot of simplifying of the constants, you get this result here. Okay, you're now in good shape to do your second integration by parts homework. I want to show you one more cool trick using integration by parts, and then we'll call it a day. Let's take a look at this integral, the integral of e to the x times the cosine of x dx, and let's see if we can't do it by integration by parts. Not at all clear what we should let u and dv equal, so I'll take a guess and I'll let u be the cosine of x, in which case dv has to be e to the x dx. We can then compute du and v as shown, and then apply the formula for integration by parts. And after doing a little simplifying, we get that our original integral is equal to e to the x times the cosine of x plus the integral of e to the x sine of x dx. And now you start to get a little suspicious. You say, I started with the integral of e to the x cosine of x. Now I've got the integral of e to the x sine of x. That certainly doesn't look easier. It also doesn't look harder. One thing you could do is go back and try letting u equal e to the x and dv being cosine of x dx. But instead of doing that, let's just forge bravely ahead and see if we can't go off on the side and compute the integral of e to the x sine of x dx using integration by parts. And I'll make the analogous choices to the ones I did the first time. I'll let u be the sine of x so that dv has to be e to the x dx. And that tells me that du is the cosine of x dx and v is equal to e to the x. Applying the formula for integration by parts, we get that the integral of e to the x sine of x dx is equal to e to the x sine of x minus the integral of e to the x cosine of x dx. And it doesn't look promising. We've now turned the integral of e to the x sine of x back into something in terms of the integral of e to the x cosine of x. Let's see what happens, though, if we substitute this result back into our original problem. And again, it still doesn't look promising. We're trying to compute the integral of e to the x cosine of x dx, and we get that it's equal to some expression minus the integral of e to the x cosine of x dx. Well, if we knew how to compute that, then we'd be done. And so it sort of looks like a dead end. Turns out that it's not. And so take a moment or two, 47 seconds, think about this, pause the video, and see if you can come up with a clever trick that might let us actually come up with an answer for this integral. And if you can't, that's okay. I just don't want to take all the fun away. So take a moment and think about it, and then we'll do it together. And the clever trick, if you came up with it, is to add the integral of e to the x cosine of x dx to both sides of this equation. If you do that, then on the left you get integral of e to the x cosine of x dx plus integral of e to the x cosine of x dx, which is just 2 times the integral of e to the x cosine of x dx. And on the right, you just get e to the x cosine of x plus e to the x sine of x, because the negative integral of e to the x cosine of x dx plus the positive integral of e to the x cosine of x dx is equal to 0. Now we're basically done. You just divide both sides by 2 and get that the integral of e to the x cosine of x dx is 1/2 times the quantity e to the x cosine of x plus e to the x sine of x, plus, of course, the usual arbitrary constant. So that's a cool, clever trick and technique and application of integration by parts. This is not your usual integration by parts problems, but sometimes you can do an integration by parts problem with a little cleverness like this. Just so you don't get nervous about it, I don't usually ask for things that are clever on quizzes and exams. I don't expect you to be able to come up with this as a trick under pressure, but you paid full price for a calculus class, so you're entitled to see this. One more interesting note about this problem, and then I'll finally shut up about it. If we had started off by choosing u equal to e to the x and dv cosine of x dx, it would have worked out exactly the same. So this is a very bizarre situation where the choice of u and dv doesn't really matter. So if you care to, give it a try. Let u be e to the x and dv be cosine of x dx. When you get the integral of e to the x sine of x dx to work out on the side, do the same thing. Let u be e to the x there as well, and you'll come to the same result. Okay, that's all I want to say about integration by parts. Go try the second integration by parts homework. You can certainly expect to have at least a couple of them where you have to do integration by parts more than once in order to complete the problem. Have fun. See you soon.